Hello, everyone. I am Suhail Sherif, and I'm going to be presenting lower bounds for higher order convex optimization. This was work done with Ankit, Robin, and Praneeth, and let's get started. So to start with, we need to find out what higher order convex optimization is. And the task of optimization is really quite simple. You have an unknown function that takes in n real numbers and outputs one real number. And your task is to find an input in the unit vol, which minimizes the value of the function, or at least up to an additive epsilon. Now, if you don't know what the function is, this is an impossible task. But we can learn about f by querying an oracle, which I'm representing by OF. So the simplest version of this oracle would be like it takes an input x, and it outputs the value of f of x. Now, even with this, it's not possible because f could arbitrarily have a very small value at some real number or at some input point. But if we make the additional assumption that f is continuous, and furthermore that the maximum derivative in any direction, the maximum slope is L0, then we actually do have an algorithm to solve this. We can just take a fine enough epsilon net, and one of those points is guaranteed to be close to the minimum. Now, before we move on to what higher order convex optimization is, let's look at a famous algorithm that operates in this framework. So gradient descent is a really popular algorithm, and it's been used, for instance, in neural networks where you have a lot of parameters, the ones underlined here. And the parameters here define a behavior of the neural network, and we want to minimize the error made by the neural network. Now, gradient descent is used when we have a lot of parameters because it has really good performance when there are a lot of parameters. We have some theoretical guarantees that back this up. For instance, if you're promised that your unknown function is convex, and you're given access to an oracle that on input x outputs the function value and a value of the gradient of f at x, then given access to this kind of an oracle, gradient descent requires only L0 by epsilon square queries. And this is a dimension-independent upper bound. So it doesn't matter even if you had a billion or a trillion parameters, you could still find an epsilon optimal solution using only these many queries. Now, gradient descent has been studied quite thoroughly. We know that despite this being a deterministic algorithm, if you have randomized algorithms or quantum algorithms that solve this task, they also need the same number of queries essentially. And when I say solve this task, I mean, again, you're promised that f is convex and you're given access to the same kind of oracle. The randomized lower bound was known for decades. The quantum lower bound we recently studied and we showed just a couple of years ago. So now we can move over to higher order convex optimization, which is pretty much the same framework. So for each natural number p, we have a different task. So let's fix some p. Fixing a p, the promise is that f is a convex function, which is p times differentiable. And its pth order derivatives are promised to be LP Lipschitz, which means that if x and y are close together, the pth order derivatives of f at x and y are also close together in the operator norm. And the query access that we're given to f is on input x, you get the value of the function and you get all of its p derivatives. Now, these are higher order tensors, and this can be very messy objects. So this is not a very practical assumption that we have access to such an oracle, but this is still interesting because of the algorithms that have come up for this kind of task. So in the setting where p is equal to 1, Nesterov showed that you can do better than gradient descent. Instead of 1 by epsilon square, you get square root of 1 by epsilon as your upper bound. And again, it was known by Nemirovsky and Newton that this is optimal, both for deterministic and for randomized algorithms. It was never studied in the quantum setting before. For the setting p equals to 2, you get an even better algorithm. That was further improved to, instead of the cube root, the 3.5th root of 1 by epsilon. And if that might seem like a weird upper bound, unfortunately, it's also optimal. So you can't do better than 3.5th root of L2 by epsilon for deterministic algorithms. It's possible, it might be possible for randomized algorithms, but we know you can't do more than polynomially better than that. And this generalizes. For a general p, you have 3p plus 1 by 2th root of 1 by epsilon. This was proven in 3 different papers, which gave 3 different algorithms and all came out at the same time. And the lower bounds from the p equal to 2 setting also carry over. And this is optimal for deterministic algorithms. And it's polynomially optimal for randomized algorithms, although there might be an improvement. Now, our contribution to this whole scene is to show that neither randomized nor quantum algorithms can do any better than deterministic algorithms. That is, we introduce quantum lower bounds in all of the settings for all p, and we improve the lower bounds, the randomized lower bounds from p equals to 2 onwards. So that's the contribution of ours. We'll now move on to the techniques that we use. So to start with, we'll look at a very convenient class of functions where it's defined, it's parameterized by a set of vectors. So let v1 to vk be unit vectors in R to the n, all mutually orthogonal, and we choose randomly from the set of possible k vectors like this. And let's assume for now that n is really large. Let's say it's 2 to the k. It doesn't need to be that, but just for simplicity of calculating, let's assume that n is 2 to the k. And the function we define is the maximum of v1 inner product x, v2 inner product x, and so on until vk inner product x. So this is the same as just taking x, viewing it in a different basis, and looking at the maximum among the first k coordinates. What we know about this is that since n is so large, it's such a large space, with high probability, each of these values is going to be exponentially small. It's going to be around 1 by square root n, and since we've assumed n is exponentially large in k, it's going to be exponentially small in k. At the same time, we know that if we choose our x carefully in the unit ball itself, we can get f of x to be -1 by square root k. That is, we choose x to be summation vi -1 by square root k times this. This is a unit vector, and it attains the value -1 by square root k. And let's set epsilon to be 1 by 2 square root k. So our task now is to find an x such that each of these values, all of them are smaller than -1 by 2 square root k. Now we know that initially all of these values are exponentially close to 0, so that's far from satisfying the epsilon optimality that we want. And when we query the oracle, what we get is vi inner product x for whichever vi maximizes it, and its gradient at that point is going to be vi. And this makes sense because if f of x is vi inner product x at some point x, then that means that at that point and in its close vicinity, f is going to be essentially just the function vi inner product x. So it doesn't matter what higher order derivatives you take, you're only going to get derivatives related to vi inner product x. You won't learn about any of the other vectors. So intuitively, you would think that you make a query, you learn one of the vi's. In your second query, you can set vi inner product x as you wish because you know vi, but all the other terms are still going to be exponentially small. And so after k-1 queries, there's still some term here that is exponentially small. And so if you're going to you still won't know any x for which say v1 inner product x is less than equal to -1 by 2 square root k. So if you've made only k-1 queries, you won't be able to output the correct answer. And this intuition does work for randomized algorithms. You can prove an omega k lower bound. But interestingly, it doesn't work for quantum algorithms, or at least we don't know how to make it work for quantum algorithms. The best we could prove was an omega square root k lower bound. It would be very interesting to see it improve to omega k. So what we had to use was a slight variant of this class of functions, where we take the max of v1 inner product x, v2 inner product x minus gamma, v3 inner product x minus 2 gamma, and so on, where gamma is some small parameter like 1 by k squared. This kind of function was introduced way back by Nemirovsky and Newton. And it's really convenient because having such a small value of gamma doesn't really change the function behavior. The minimum value is still approximately the same. And with the same value of epsilon, the task that we are faced with is again the same. We want to find an x for which all of these components are less than equal to -1 by 2 square root k. The way this is different from the previous function is that we're going to learn all the vectors in order. In our first query, all of these are going to be exponentially small, but the second term as a whole is going to be exponentially close to minus gamma. The third term will be exponentially close to -2 gamma, and so on. So the maximum is going to be the first term. So we learned V1 in the first query. In the second query, we know V1, we can set it as we want, but the second term is still going to be larger than all of the later terms, so we'll only learn the second term, and so on. So with k-1 queries, we still don't know what Vk is. And if you don't know what Vk is still uniformly random from a large space, you can't make this not be exponentially close to 0, and so you still won't be able to solve the task. Now, this was a bit informal, this don't know Vk part, but you can make it formal using the hybrid argument. It's like this function class was made for the hybrid argument. And that works through taking these corrupted functions. So this function just takes the maximum of the first I terms. And the point is that if I give you access to these corrupted oracles, then you can formally state that, yes, I don't know anything about vi plus 1 because the oracle itself didn't know anything about vi plus 1, apart from the fact that it's orthogonal to the first type vectors. And on the other hand, if you get an answer among your first I queries from the oracle for f less than equal to I, actually I should correct that. In your first I minus 1 queries, if you get an oracle answer from f less than equal to I, you're not going to notice the difference because vi inner product x minus I minus 1 times gamma is still going to be larger than all of the later terms. So the maximum of f is going to be with high probability the same as the maximum of f less than equal to I. And so using this logic, you're not noticing the difference between corrupted oracles and the original oracle. So your output using the corrupted oracles is going to be very similar to your output using the original oracles. And with the corrupted oracles, you know that you're not getting the correct answer because you actually don't know Vk at the end of your algorithm. And this works for quantum algorithms and randomized algorithms as well. And this is how we proved our gradient descent lower bound. But now we want our higher order convex optimization lower bound. So what we want to do is we want to change this class of functions, which wasn't even differentiable, into smooth functions. And the way we're going to do that is to create just a smooth version of the previous function class. If your function was non-differentiable, then you can imagine you've taken some sandpaper and you've just smoothened out the non-differentiable part, and you now have a smooth function. Ideally, you've done it better than I have. And we wanted to retain the sequential property that we learn V1 in your first query, V2 in your second query, and so on, so that we can still use the hybrid argument and get the same lower bound. But when we're doing this kind of smoothing, your gradient is quickly changing from one value to another value in a short span of time. So your higher order derivatives are going to be large if it looks similar to our previous function class. And if we can manage this while keeping the higher order derivatives with the LP constant at most k to the 3p by 2, we'll get exactly the lower bound that we were looking for. So this is what we're really trying to do. And this whole lower bound idea that we've spoken about till now, it didn't need n to be exponentially large. N could just be around k cubed, and gamma could be around 1 by k to the 3 by 2. This is important because we're actually going to show that LP is approximately gamma to the minus p. We're going to smooth it in such a way that LP is approximately gamma to the minus p. And that's exactly what we wanted. So we don't need to worry about the nasty 3 by 2 and stuff. We just need to compare it to gamma. All right, so how do we do this? How do we do the smoothing? So let's take a place of non-differentiability. What we analyzed was that this value here with high probability is going to be around gamma more than this value here. So that means that your first query is happening far away from the place where they meet. Your first query is happening somewhere here. So you can change the function around here. Your first query is only going to learn the value of V1, and you'll still have sequentiality. So that works well. So how do you do the smoothing? You just convolve it with a ball of a small radius. And it's going to look like this. It's going to be the red curve, it switches to purple, and then over to blue. And if eta, the radius of the ball, is much smaller than gamma, it's only changing it in a small region around here, and that doesn't change what you see when you do your first query. So that's amazing. The lower bound still holds. The convolution, this operation, it retains the smoothness of the original function, and it adds an extra level of differentiability. But the problem is that when you add this extra level of differentiability, so here it wasn't differentiable, it became once differentiable, but the L1 constant gets a hit. It becomes L0 times n by eta. If it was just 1 by eta, then we could do it p times, get p times differentiable function, with smoothness 1 by eta to the p, and we'd be done. But because of the n, this doesn't work. So we need another trick here, which we do in the form of softmax. The softmax function is a function that approximates max, and it has a parameter rho. As you decrease that parameter rho closer to 0, it becomes a better approximation to max. And this function is convex, it's infinitely differentiable, and its LP constant is just rho to the minus p. The problem with it is that it changes the function value everywhere. Even here, the purple line is actually above the red line. So when you query it, you're not going to get the red line. You'll actually be learning something about V2. And that completely decimates our lower bound approach, because for the hybrid argument, we want it to actually not notice a difference between the corrupted version and the actual version. However, it's still useful, because if you take rho to be something like gamma by 10p log n, then in the places where our first query was happening, the purple value is very slightly smaller than the red value, just n to the minus 4p larger. So if you just take the maximum of the red line and the softmax curve, but just bring the softmax curve down a little bit, then our first query is still going to find out just the red value. It's still going to learn V1 and nothing about V2. So we get back that property. The problem is that this is no longer smooth. It's not even differentiable. But it's really close to being smooth. It's pretty much the softmax function plus this correction. And this correction is very close to just the 0 function. In fact, it's a function which has a very small L0 constant, around n to the minus 2p. And this is all that we need, because now when we smooth this function, if we do randomized smoothing p times, well, we get softmax had this LP constant. Our non-differentiable part here, the red part, when smooth p times, it has this LP constant, the original L0 constant times n by eta to the p. But the L0 constant is so small that it completely swallows up the n by eta to the p. And that is not relevant to us when we're looking at what the LP constant is. And since rho was around gamma by log n, rho to the minus p is just gamma to the minus p times log n to the p, which is exactly what we wanted. We wanted k to the 3p by 2, and except for the log n part. And the lower bound that we actually get from this is the lower bound, the optimal lower bound, but except for this log of LP by epsilon to the power minus 2 by 3. So just to recap, our final function, it's the maximum of softmaxes, which each softmax move down a little bit. And then you take this and you convolve it p times, and you get your final highly smooth function for which you can use the hybrid argument. And in the hybrid argument, the intermediate functions that you have are just, you take the maximum of the first I terms, and then you convolve it p times, and that'll be your ith intermediate function. And that ends the lower bound. The open problems that I have to that are interesting here are, what is the quantum complexity of optimizing this function class that came up before? What is the complexity of this optimization if your oracle is only giving you, say, the function value and gradient value, but you're promised that your function is highly smooth? This is still a setting that has not been studied even in the randomized or deterministic setting. And are there other unexplored areas where, you know, we can use the hybrid argument to guide ourselves to construct a lower bound instance? If you weren't trying to prove a quantum lower bound here, we probably wouldn't have even ended with a randomized lower bound, because we would have deviated somewhere and ended up in some complicated function class. So that really helped us sticking to the hybrid argument. And that's my talk. Thank you for your attention. Goodbye.